Next, let us consider the case n equal to 1. So, now we are talking about non-axisymmetric modes, of course, because there is theta dependence. As soon as n is non-zero, we have theta dependence. So, in that case, if you substitute n equal to 1 in the characteristic equation, once again you will find that the first solution is omega equal to 0. So, this is one solution for n equal to 1, omega equal to 0 is again a solution. So, that you can see directly from here once again. So, if n is equal to 1, so this term drops out in the characteristic equation. So, once again omega equal to 0 is a solution, and then there is another solution which can be determined from here. So, the first solution is omega equal to 0. Again we suspect that this is a rigid body mode, which it is. So, if you calculate once again the eigen vectors, they turn out to be I and 1. So, let us see what this means. So, this gets multiplied, the eigen functions are nothing but so these are the eigen functions, and that can be written as so, if you consider this this solution, then let us see how is the deformation. So, this is the ring. So, now, so this is the deflection of the center the neutral fiber. Now, sin theta with a negative. So, this implies that so this is the theta equal to 0, this is the datum. So, this is u, this is the u motion, and this is the w motion. So, u is 0 here, whereas w is plus 1, and then you will find that at this point theta equal to pi by 2. So, this is minus 1. Now, minus 1 would mean, because the axis here is like this, so minus 1 would mean this, and similarly you can find out that this represents a motion like this, and similarly this eigen function vector will represent a motion like this. So, these are nothing but the rigid body modes in the x direction and in the y direction. So, these are again rigid body modes which imply linear momentum conservation. Now, let us consider the other solution for n equal to 1. We saw that there are two solutions, one was 0, the other one turns out to be this, and the eigen so for this the eigen vectors happen to be given by this complex notation. So, this turns out to be following this notation. So, if you multiply this with exponential I theta. So, here we have so, these are the eigen function vectors. Now, here now in every so these are actually the non-dimensional frequencies. If you want to find out the dimensional frequencies, they are given by so these are the dimensional frequencies. So, these are the eigen functions that we have for this mode. Now, let us have a look at this mode. So, this shows the mode because of some aspect ratio problem. It might seem a little like an ellipse, but actually this dashed one is actually a circle, which is the undeformed position of the ring. Now, here you and this black one shows the mode corresponding to the imaginary part, as you can see here. So, let us understand this motion before we look at this picture again. So, let us consider this imaginary part. So, once again let me draw the ring. So, if you consider this imaginary part of the solution, so this as the eigen function. So, the motion can be written as where omega is of course given by this eigenfrequency, circular eigenfrequency. Now, so in the circumferential direction you have this as sin theta. So, which means here there is no circumferential motion, but there is this radial motion. Here you have circumferential motion as you increase. So, you have circumferential motion here, the circumferential motion is the maximum, which is positive plus 1. So, in this direction, and when you come here this motion is purely radial, there is no circumferential motion at this point. Similarly, you have circumferential motion in the negative direction here at this point and no radial motion here. So, which means that you expect the ring to so the center line of the ring will look like this. It seems that the center, that at least the geometric center of the figure has shifted. I mean, this is an exaggerated figure, of course. It seems that the geometric center has shifted, but actually the center of gravity of the ring is not shifting because of a combination of radial and circumferential motion. So, the particles are actually moving in this direction circumferentially, while radial motion is like this. So, we will look at this figure once again now. So, here you can see this is the undeformed ring, and I have drawn these empty circles to indicate the particles before deformation, and these filled circles are these particles after, or these material points after deformation. So, you can see that there is a clustering of these material points here. So, you have compression here and rarefaction here, so that finally it is a momentum conserved mode. So, continuing this way you can then solve for higher modes, but then let us see something interesting. Now, we have discussed as yet till now this mode, which was the breathing mode, and this mode, but they are not the lowest modes. The lowest mode appears to be like this. Once again there is some aspect ratio problem. So, this dashed one is the undeformed ring, and this is the deformed configuration. So, you see this this in this mode it is moving out here and moving in here, and vice versa. So, this is going to oscillate like this, and so there is a phase difference of between this and this, which is pi. Here you have the higher mode. So, you can see the circular eigenfrequency non-dimensional. This is the next higher, and this is the fourth mode, and this is the fifth mode, and so on. So, you can calculate all the eigen frequencies of various modes and also plot the eigen functions. Now, looking at these figures, it might seem that these are nodal points, but this has to be checked properly, because now we have not only radial motion, but also circumferential motion. So, if a node is considered to be a point at which there is no motion, then this might not be a node. For example, here this is definitely not a node. So, occurrence of actual nodes has to be checked by looking at motion of material points on the ring. So, till now we have been discussing about vibrations of rings. Next we will discuss vibrations of arches. So, circular arches. So, a circular arch is nothing but a sector of a ring. We will consider two examples of arches. One is the pinned arch and clamped. Now, as you will realize that the equations of motion for the arches for the curved beams, they are coupled and complicated. So, what we are going to do for the case of arches is that we are going to solve this approximately using the Ritz procedure. So, let us see what are the boundary conditions, because we need to choose admissible functions for application in the Ritz method. So, let us look at first the pinned arch. So, this is a schematic representation of a pinned semicircular arch. Now, the boundary conditions if you look back on the discussions we had on the boundary conditions of the curved beams, then at theta equal to 0 and theta equal to pi, we must have u equal to 0, which is the circumferential motion, and w equal to 0, and we also must have so we have 6 boundary conditions as we had discussed. So, here we have 0 displacement at these 2 points, and this is the 0 moment condition at these 2 ends. Now, so we have these as the geometric boundary conditions. So, to choose now we have to choose admissible functions. So, we can choose admissible functions. So, we expand our field variables. So, the way I have chosen for this problem, so the first admissible function, so this is 0 at theta equal to 0 and also 0 at theta equal to pi. So, I can now construct so, I have taken a 3 term expansion for u and similarly a 3 term expansion for w using the same admissible functions. Now, these expansions we substitute in the Lagrangian. So, we have a semicircular arch. So, 0 to pi So, this is our Lagrangian. So, we substitute these expansions here and do the integration over theta, and finally, we obtain the discretized equation of motion in terms of these coordinates a. So, we will obtain where these vector a is a1 to a6, and we can perform the modal analysis and obtain the circular eigenfrequencies. So, for this arch pinned arch, the non dimensional circular the first two non dimensional circular eigenfrequencies are obtained as. Now, from here you can calculate the dimensional circular eigenfrequency. Now, this figure shows the first two modes of vibration of the pinned arch. So, you can see that so this is the unsymmetric mode and this is the symmetric vibration mode, which is having a higher frequency. Now, in a similar manner you can perform for a clamped arch. So, this is a clamped arch. Here the boundary conditions at zero and pi happen to be like this. Now, here all the boundary conditions are geometric boundary conditions. So, in view of this, we have this expansion Now, here because you have this slope condition as well. So, del w del theta condition. So, the admissible functions for w must be taken like this. So, theta square pi minus theta whole square. So, if you once again substitute this in the expansion and calculate the discretized equation of motion and further calculate the eigen frequencies, they turn out to be. So, the non-dimensional circular eigen frequencies appear as so, these are higher than the pinned case as we expect. So, here this figure shows the modes of vibration. Again, this first mode is the unsymmetric mode and this is the symmetric mode with higher frequency. So, let us recapitulate what we have discussed today. We discussed the vibrations of rings and arches. So, we have looked at some interesting results in the vibrations of rings and we have considered two kinds of semicircular arches, and using Ritz method we have determined the eigen frequencies and modes of vibrations. So, with that I conclude this lecture.